So to start us off for homework 11, there's a couple things that I want to take a couple notes on. One of them being the zero product rule thing here. We'll make sense of that, and then we'll come back to homework 11 and do some stuff there. So ignore the fact that this says exam 2 answers at the top or solutions or whatever it says. This is just a blank page that I have here for the purpose of taking some notes. And so we, in lesson 11, are working on finding solutions to quadratic equations. And so what ends up happening with a quadratic equation is it is either a sad face, like this graph right here, or it is a happy face, like this red graph right here. And so the thing to understand at this point is that when these blue or red lines cross the x-axis, that is what we consider to be a solution to a quadratic equation. And so what you'll notice about all of these solutions to these quadratic equations is that the y value there is equal to 0, meaning that the blue or the red line is crossing the x-axis. And so that's not something that's super important to understand now, but it does provide a little bit of context for why we're doing what we're doing. We're going to be trying to set each of these equations equal to 0 and find the solutions, because that would tell us when everything is equal to 0, where those lines will be crossing the x-axis, which again is what the solution is. Now, going back to that whole A-B rule that we saw on the actual homework assignment. First of all, I need you to understand that A and B are not referencing this. The AB that they're talking about here is not referencing this A, this B, and this C. It is something totally different. So I'm actually going to rename the AB rule to be the JK rule, just to avoid confusion of A, B, and C. And so what the JK rule says is if J times K is equal to 0, either J is equal to 0 or K is equal to 0, or both. J and K are equal to 0. Now the reason that this is important is because when we're working with these quadratics, we've done some work around factoring, and we hopefully have gotten pretty good at factoring. But we need to recognize that if once we factor it, if any part that we have factored out is equal to 0 and being multiplied by the other part, the whole thing is equal to 0, and it would make the equation true. That's a kind of a weird way to say it without any context. We'll get some context in a moment. So to start with, let's just have a quick understanding that if I had JK equal to 0, and I assigned a value of 5 to J, and I was multiplying that by K, and it was equal to 0, we can see that K would have to be 0. That's the only number that would make 5 times K true, is if K was equal to 0. Also, similarly with the JK rule, if we said that I wanted to replace K with 8, and I ended up with J times 8 is equal to 0. The only possibility would be that J would be equal to 0, because 0 times 8 is the only thing that makes 0. And so really what they call the AB rule and what I'm calling the JK rule is saying is that when we multiply two things together, if either one of them is 0 or both of them is 0, the whole thing will be 0. So that brings us back to today's homework assignment. And what I just described is all that stuff at the top, the zero product rule. They use AB, I use JK, same thing. But let's check out how that applies to finding a solution to a quadratic. And so the problem is right now I could Like if I wanted to solve this using the old school methods or whatever, I could say, oh, I'm going to add 15v to both sides, and I would have 5v squared equals 15v. And then I would look at that and I would go, gee, I don't know what to do next. Well, that's because that's not how we solve quadratics at all. So today we're going to be talking about a new method for solving using kind of what we discussed in the JK rule a moment ago. So the very first thing we're going to do when we want to solve a quadratic or anything that has an exponent to the value of 2 right there is we want to factor it completely. So I'm going to recognize that both 5v squared and negative 15v share a 5v. And if I factor that out, I'm left with 5v times v minus 3. Now, my description a little bit ago would be that the 5v is the j, and the v minus 3 is the k. And if we remember, if I have j multiplied by k equals 0, either j has to be 0 or k has to be 0, or both of them could be 0. And so the process for solving a quadratic is going to be to figure out, gee, how could I turn j into a 0? And how could I turn k into a 0? So what we need to do that is to treat these as two separate parts now that we have factored them. And so we're going to say, well, what if I wanted to turn 5v into 0? And what if I wanted to turn v minus 3 into 0 to be able to make this whole thing a true statement? So to do that, we will separate them out and ask the question, gee, let me actually ask the question because that's a good idea. Gee, what makes 5v equal to 0? And then the other question is, gee, what makes v minus 3 equal to 0? Because if the green one, the 5v, or the blue one, 5v minus or v minus 3 is equal to 0, that whole left side will be equal to 0 because anything multiplied by 0 is equal to 0. So to answer that question, we're going to just do it. Gee, what makes 5v equal to 0? And we would go ahead and divide by 5 on both sides. And we would see that if v is equal to 0, then 5v is equal to 0. And at the same time, we need to answer the question, gee, what makes v minus 3 equal to 0? Well, we would add 3 to both sides. And we would see that when v is equal to 3, the quantity v minus 3 is equal to 0 because 3 minus 3 makes 0. So what this is really telling us is, hey, if I was to put 0 back into the original equation, I would end up with 0 equals 0. And if I was to put v equals 3 back into the original equation, I would end up with 0 equals 0. Let's test it, but instead of using the original equation, I'm going to use this because it will demonstrate it a little bit better, recognizing that that is equivalent to what we started with. It's just in factored form. And so what I'm going to do, now recognize that this is the answer. V equals 0 is an answer, and v equals 3 is an answer. So to finish this off, we would say v equals 0 or v equals 3. And it says in the directions here we can separate our answer by commas. It may be the case that the way Alex wants you to provide your answer is to go like this, v equals 0, 3, which I don't like because that now looks like a point on a grid, and that's not what I want. What I want is that the understanding that those are both answers. 0 is an answer, 3 is an answer. So I very much prefer writing it like this, but I'm not exactly sure what Alex is going to require of you. So that being said, let's test it. And so we are done with the problem, but we're going to test it. A better word here is check. So if I was to take 5v, v minus 3 equals 0. And we're going to do this twice because we've got two things that we think could be an answer. If I was to test the 0, so we're going to put 0 in for v. Let's see if it comes out to be a true statement. 5 times 0 is 0. 0 minus 3 is negative 3. And 0 times negative 3 is 0. So if we put 0 in, it causes the 5v to become 0, which causes the entire left side to become 0. Let's test that now for the v minus 3, where we had v is equal to 3. If we put a 3 in there, I need to put a 3 in front as well. We would have 5 times 3 times 3 minus 3. 5 times 3 is 15. 3 minus 3 is 0. And 15 times 0 is 0. So we can see again that 0 is equal to 0. And so we could put either the value 0 or the value 3 back into what we started with, and we would end up with a true statement of 0 equals 0. Now again, I'm going to highlight the 5v was our green one, and the v minus 3 was our blue one. The way that we got there was we factored the original quadratic into its parts, and we need to recognize that if we can turn the green part into 0, that whole left side will be equal to 0. And if we can turn the blue part, the v minus 3, into 0, that whole left side will end up being 0. And that's demonstrated down there in the check, where we can see again that if I put 0 in for v, I end up with something that's going to make 0. And if we put 3 in for v, we're going to end up with something that makes 0. That was a long explanation for number 1. I'm going to go a little bit faster on the ones that follow, but I hope that this helped make sense of what we are doing and why it works. This always seemed like a magic trick to me when I was a student, but I hope this helps build some understanding. Again, that back up here at the top, if we can turn that green piece into 0, the whole left side will be equal to 0. And if we can turn that blue piece into 0, that whole left side will be equal to 0, because 0 times anything makes 0. Okay, on to number 2. So I'm going to assume that we're pretty good at factoring at this point. And I don't know what just happened with my little thingy. So we're going to take this and recognize that the AC method, 1 times 12 makes 12. Factors of 12 are 1 and 12, 2 and 6, and 3 and 4. I need factors of 12 that will make a positive 1. So that will be a plus 4 and a minus 3. So we will split this up, y squared plus 4y minus 3y minus 12 is equal to 0. We do our down the middle. And on the left, we can factor out a y. That leaves y plus 4. On the right, I want to end up with y plus 4, so I need to recognize that I need to factor out a negative 3, so that what's left inside will be y plus 4. And all of that is equal to 0. So again, we can factor out, as we've done in the past. The y plus 4s are the same. They will be factored out. There's our y plus 4. And what remains is a y minus 3. And that whole shebang is equal to 0. Now, as we did with the last problem, I'm going to demonstrate something using colors. If we have y plus 4, and we have y minus 3. Again, the green and the blue one. If I can make the green one equal to 0, 0 times y minus 3 will be 0. If I can make the blue one equal to 0, 0 times y plus 4 will also be 0. So if either one of those, the green one or the blue one, are equal to 0, that whole left side will be equal to 0. So we're going to split it into its parts as we did last time. We'll get a y plus 4 is equal to 0. We're going to see what it takes to make the green one 0. We're going to get a y minus 3 is equal to 0. We're going to see what it takes to make the blue one equal to 0. And so what we would need to do is here subtract 4, subtract 4. We can see that when y is equal to negative 4, the green part of this would be equal to 0, which would make that whole left side equal to 0. And then the right side, the blue part, we end up with y is equal to 3. And so if we put a 3 in there, that whole left side would turn into 0, and we would have our solution. So again, as I mentioned in the last problem, the way that I like to do this is y is equal to negative 4, or y is equal to 3. Again, Alex may require you to do this by using commas or something, but I'm not a huge fan of that. We can check really quick. Again, we'll just throw negative 4 in there and throw 3 in there and see what happens. This time, instead of using the factored form, I will use the original equation just to show that that does indeed work. And so we're going to check for the value y equals negative 4. And so if we take y squared plus 4, y minus 12 equals 0, we're going to put a negative 4 in there. Negative 4 squared makes 16. And then the signs will turn into a minus 4, minus 12. 16 minus 4 is 12. And 12 minus 12 is 0. So negative 4 does work. Negative 4 is a solution. And we're also going to check y equals 3. So again, our original equation, y squared plus y minus 12 equals 0. If we put a 3 in there, three squared is 9, plus 3 minus 12, 0. And 12 minus 12, again, 0 is equal to 0. So the check is not necessary for you to do. I'm just doing that to demonstrate that those solutions both work and kind of hopefully bring some understanding to why those solutions work. And so, again, we can, I'm going to highlight here, we can turn the green part of this equation into 0, and that will make that whole left side equal to 0, or we can turn the blue highlighted part of this equation equal to 0, and that will make that whole left side of the equation equal to 0, because the green one times the blue one, if either the green one or the blue one are 0, it makes 0 on that left side. Okay, and on to number 3. So something unique about number 3 is that this time we don't have it equal to 0. Now that's a problem, and it's a simple problem to fix. So the first step in any of these that are not already equal to 0 is going to be to make them equal to 0. So let's do that. The way that we would make this equal to 0 is by moving that negative 5 on the right over to the left side. So we got to add 5 to both sides. And we've got 3v squared plus 16v plus 5 equals 0. Now we need things to be equal to 0 because it's one of the only things that we can say for sure. If I multiply by 0, I'm going to get 0. Like I can multiply some number by 2 and I don't know what I'm going to get unless I know what the original number is. I can say that I can multiply any number by 0 and I'm going to get 0. And that's why setting these equal to 0 is helpful and a big deal. So first off, factoring by grouping, I need the AC method. My A term is 3, my C term is 5, so 3 times 5 makes 15. I need factors of 15 that will make 16. Factors of 15 are 1 and 15, 3 and 5. Positive 1 and positive 15 will both do that. So we will do that. 3v to the power of 2 plus 15v plus 1 more v plus 5 equals 0. And so that 15v and that 1v in the middle there will make 16v. Do the da-da-da-da-da. On the left side, I can factor out a 3v. And on the right side, I can factor out a 1. Kind of weird to factor out a 1, but taking a 1 out is the only thing that will make a v plus 5 so that our two sides match. And then remembering that since they both have a v plus 5, we can factor out the v plus 5. And what's left is 3v plus 1. Now, similar to previous problems, we have what I'm going to make a green part and a blue part. If the green part is equal to 0, then the whole left side will be equal to 0. If the blue part is equal to 0, then the whole left side will be equal to 0, and either of those would create a true equation. So what we need to do is figure out how could I turn v plus 5 into 0? And how could I turn 3v plus 1 into 0? We just need to solve those. So subtract 5, subtract 5. We got v is equal to negative 5. And 3v plus 1, we've got to subtract 1, subtract 1. And we get 3v, is equal to negative 1. And then to finish it off, we would have to divide by 3 and get v is equal to negative 1/3. I love fractions. Not? How about you? Okay. And so we are going to end up with a negative 5 and a negative 1/3 as our solution. And so the way that I would personally write this is v is equal to negative 5 or v is equal to negative 1/3. Now I could go back and test these to see if they're going to work, but there's a fraction there, and I don't want to do that. I know I did it correctly, but again, recognize that if we were to take the negative 5 and put it into the green part of what we had there on the left, negative 5 plus 5 does make 0, and so that would cause the whole thing to become 0. And the negative 1/3, if we put it into the blue one, the 3v plus 1, that would also make 0, which would make the whole thing 0. But for our purposes, we know that we did it right. That's the way we go about this. We're moving on to number 4. Okay, and so number 4 looks particularly nasty. Remember, there's one trick to this, and that trick is to have everything equal to 0. And so what I need to do first, I'm going to, on the right side there, expand it out, multiply the v plus 4 times the v plus 4. And so I'm going to do that work over here on the side. V plus 4, v plus 4. I like to use a box method to do this. It's just a really easy way for me to multiply. V times v is v squared. That's 4v. That's 4v. That's 16. So I'm going to rewrite this with that expanded out for me. So 2v to the power of 2 plus 4v plus 11 is equal to v squared. And I can recognize that those two are going to add together to make 8v. So plus 8v plus 16. Now you might be thinking, geez, look, you just made it worse. But remember, what we need is one side of our equation to be equal to 0. And so I'll make the right side equal to 0 by subtracting v squared. I'll get v squared plus 4v plus 11 is equal to 8v plus 16. My next step will be to subtract 8v. Now we get v squared minus 4v plus 11 is equal to 16. My last step will be to subtract 16. And we will get v squared minus 4v minus 5 is equal to 16 minus 16 is 0. And so now we're at the place where we can begin to figure out what the values of v that would make this true are. And so again, the process for this is saying, okay, I don't care what I've got or what is given to me. If it is something that is to the power of 2, I want one of the sides of the equation to be equal to 0. We just did the work to make that happen. Now we can factor the left side and figure out what values that could be. So the AC method, 1 times 5 is 5. The only factors of 5 are 1 and 5. And so I need a negative 4, so I will need a positive 1 and a negative 5. So v to the power of 2 plus 1v minus 5v minus 5 is equal to 0. And so factoring, like we've done in the past, down the middle. On the left side, I could take out a v. And I'm left with v plus 1. On the right side, I want a v plus 1, so I'm going to factor out a negative 5. And now recognizing that I've got a v plus 1 in both of those, we can factor the v plus 1 out. And what remains is v minus 5, or plus a negative 5, which would eventually become v minus 5 anyway, so I'll just write it that way to start with. Now, again, it's important to remember that we have two pieces there on the left. We have a v plus 1, and we have a v minus 5. They are being multiplied together, so if v plus 1 was to be 0, that would make the whole left side 0. And if v minus 5 was to be 0, that would make the whole left side 0 as well. So we need to see what is it that makes v plus 1 equal to 0, and what is it that makes v minus 5 equal to 0. And so on the left side, on the green one, I would subtract 1. V is equal to negative 1. And on the blue one, add 5. V is equal to 5. So the solution for this one is that v is equal to negative 1, or v is equal to 5. And we could go through the process of checking. Don't have any fractions this time, so I wouldn't mind checking. But that would be a ton of work to put that back into what's up there at the top, and I don't see any purpose in doing that, honestly. But again, this is the process that we go through to find the solution to a quadratic equation, or the solutions, more than one, to a quadratic equation. And it entails getting one side of the equation equal to 0, and then factoring the other side and seeing what we would have to have as our values for our variable to make it a true equation. Okay, on to number 5. And so for number 5, I've always found these to be kind of fun, but a little bit challenging at the same time. So the length of a rectangle is 1 meter less than twice its width. So we can say that the length is 1 less, so subtract 1 twice the width. So length is 2 times the width minus 1. And the area of the rectangle is 21 meters squared. So then we have to remember and kind of puzzle through. It's a bit of a puzzle and say, gee, area is length times width for a rectangle. And in this case, we know the length is 2w minus 1, but we don't know the w. And so what we are actually wanting to do is replace L with 2w minus 1. And I'll explain why. Because now on the right side of this equation, we only have w's. And so we can do stuff with this now that we couldn't do before because we had an L and a W. We also have an A, but we know what the A is. And so at this point, we're also going to replace the A, the area. The area is 21. And so as I've said before, when we're finding solutions to a quadratic, we need one side of the equation to be equal to 0. This doesn't look like a quadratic yet because we don't have an exponent to the power of 2 anywhere. But let's see what happens when we simplify the right side. So that w is going to be distributed to the 2w and to the minus 1. And we're going to get 21 is equal to 2w squared minus w. Now that gave us that squared that we needed to clue in to be like, hey, this is a quadratic. And so we're trying to find the solution to the quadratic. So we need one side of this equation to be equal to 0. So let's make the left side of the equation equal to 0 by subtracting 21. We've got 0 is equal to 2w to the power of 2 minus w minus 21. Now we can do exactly what we've been doing so far and factor this thing and set those pieces that we get equal to 0. And that will give us our solution. So AC method, 2 times 1 is 42. Factors of 42 are 1 and 21. No. 1 and 42. 2 and 21. 3 and 14. 6 and 7. And so we need factors that when we put them together will make a negative 1 for that middle term, that negative w in the middle. That's going to be a positive 6 and a negative 7. So 2w to the power of 2. I need a positive 6w and a negative 7w. So that when they combine, they would make that negative w. Now we do our da-da-da-da. And we can see that on the left, I could factor out a 2w. And be left with w plus 3. And on the right, I want a w plus 3, so I'm going to factor out a negative 7, which gives me a w plus 3. And so we can recognize the w plus 3s are common to both, so they will factor out. My arrows are a little bit off, but that's all right. And then what remains is a 2w plus a negative 7, and I'm just going to write that straight up as a 2w minus 7. And so now, exactly how I've done in the past, if the green one is equal to 0, or the blue one is equal to 0, that whole right side is also equal to 0. And so we're going to ask ourselves the question, gee, how do I turn the green one into 0? And how do I turn the blue one into 0? And so for the green one, we got to subtract 3, subtract 3. Negative 3 is equal to w. And for the blue one, we have to add 7. And we get 7 is equal to 2w. Then we get to divide by 2. And we could leave it as 7 halves. I'm going to change it to be 3.5 is equal to w. Now recognize we are talking about the area of a rectangle here, so there are two solutions where w is equal to negative 3 or w is equal to 3.5. But we have to strike the w is equal to negative 3 because negative distances don't exist in real life. So the only answer that works in real life here is the 3.5, not the negative 3. Even though mathematically negative 3 is an answer, it's not something that is appropriate for the context of this problem. So we know that the width now is 3.5. So we're going to highlight that guy, I don't know, yellow, I guess. So our width is 3.5. Coming back up to our length, we knew that our length was 2w minus 1. And so we're going to use those facts to find our length. So L is equal to 2w minus 1. L is equal to 2 times 3.5 minus 1. And L is equal to 7 minus 1, so L is equal to 6. Now we have a length and a width for this thing, where the length is 6 and the width is 3.5. And if we were to multiply those to check, 6 times 3.5, is it 21, which was our area? Yes, it is. And so the length is equal to 6. The width is equal to 3.5. And I should go ahead and put meters on there. I'm kind of bad about labeling my answers. But that's going to be it for homework number 11. This is kind of a haymaker, this one. This homework assignment is pretty serious, so I'll be glad to help in any way I can. I hope that this video is helpful, and I hope that you have an awesome day.